So we can sort of do this again, right? So if we look at, now I've taken the numbers up here and I've simplified them by multiplying on uh, the number 2n plus 1. And now I look again for patterns. What sort of comes to mind here is the primes 29, 23, 17, 11. So you see there's exactly 6 between these primes, and that makes me think that in some systematic way we are encountering numbers that are jumping with 3 at a time. So of course I need an explanation here that the number halfway between 23 and 29 is 26, and I don't see the 2, but at least I see the 13, so I think that somehow is a reasonable assumption. So if we write them up again, so I have the index next to the value so I don't get lost here, then the point is that I need to multiply the index by 3 and subtract 1. Right? So I will take this number here and I will divide it by 3n minus 1, and then I get something like this, which again maybe looks a little bit complicated, but let me just write it out without doing the I factor. And if I write it out using the I factor, then there's something that sort of comes to mind here, and that is that the numbers that we're seeing here tend to have fairly large common denominators. So I mean, I have an 8 and an 8, I have a 17 and a 7 and a 14, I have a 5 and a 10. So in order to try to get rid of the denominator, I will just multiply on straightforward an n. So let me do that here. I'm multiplying on the n. Now I have something which is fairly close to being an integer now. I just sometimes divide by 2. So I will, instead of multiplying on with n, I will multiply on with 2n. What I'm doing here is actually slightly different from what I'm doing in the book. And every time I do this, something slightly different comes out because it's different what I notice in what order. But you know what, this will work. Okay, so now you see I've multiplied the original fractions by 2 times n times 2n plus 1 divided by 3n minus 1. So some complicated number there. And then I'm back to having an integer. So the important observation here is now I have an integer, and actually the pattern here is fairly straightforward because there's a jump of 9 between these values. Right? So in order to get the right thing, I need to multiply it by 9. So here I would get 18, here I would get 27, here I would get 36. So I just need to subtract 6 from that. So I'm comparing the observations I had here with 9n minus 6, and it's exactly the right thing. So if I was to sort of go back, backtrack my computation, I will instead of multiplying on by these numbers, I will divide by them, and so that gives me exactly the correct numbers, right? So I was looking originally at Cn plus 2 divided by Cn plus 1, which is actually Cn plus 1 divided by Cn. I get this information here, and I've now found a formula that generates the exact same sequence of fractions. That is probably not a coincidence, and hopefully I can use this in order to make a real proof concerning these issues here. But of course, this was a theory about what is the form of the successive quotient, right? So I could try to take this expression and ask Mabel to simplify it. I get something that looks like this. So my hypothesis is that the successive quotients between the CNs is this expression, which is a rational expression which has a quadratic expression in both the numerator and the denominator. And then, of course, if my hypothesis is that the successive quotients is this fraction there, then I can go back to an expression for the original numbers by multiplying them together. just as I would with the factorial, if I had gotten the successive quotients to be 1, 2, 3, 4, and so on, then going back to the original would be multiplying these together, right? It's like having successive differences. You come back using the sum. Here I have successive quotients, so I come back using the product. And I can ask Maple to do this for me. I do the product, and I plug it in. But then when I'm asking Maple to check that I get the right thing, I run into problems. So Maple is not willing to do this computation for me. And that has to do with the fact that I put a capital P up here. And I put a capital P up here in order to ask Maple to not try to simplify this expression. So Maple has these inert versions of product and sum, which lets them an integral, which lets them sort of keep the expression as it is and doesn't try to simplify it. And the reason why I did that is that if you do ask it to simplify it, you'll get something complicated with the gamma function. And we'll be able to do this in a much nicer way, but let's live with this for now. And then you can see that if I check this observation toward against my original C, I get the right thing. Right? I almost get the right thing because there's an issue here at the very beginning. And also this expression I've gotten here isn't super helpful. I'm sure it would be nice to have something slightly less complicated. And we'll see when we get to the more advanced ways of doing symbolic inversion that we'll be led to something much nicer than that. But at least I've sort of shown you the ad hoc procedure of taking a sequence of integers and then trying to analyze it basically by looking at the prime factorization of the numbers. And this is something that works surprisingly well in a lot of situations. And then, of course, at the end of that, you haven't really created any mathematics, right? You've just created an advanced theory about what these numbers may be, but hopefully the advanced theory that you have generated will somehow help you prove things about this sequence. So that's the key idea.